Welcome to the deep dive. We're here to cut through the noise and get right to what matters. And today, we're doing something a bit different. Our source material isn't the usual reporter article. Nope. We're looking at selected questions from the JN0-481 exam, Data Center Specialist Practice Questions. Now, wait. Don't tune out. We're definitely not giving you a test. Our mission here is to use these, well, seemingly very technical questions, almost like a magnifying glass. They give us this unique lens to unpack some really crucial real-world stuff happening in modern data center networking. Think of it like a shortcut, maybe, to getting properly clued in on a topic that can feel, honestly, a bit overwhelming otherwise.
That's a great way to put it. And just for a little context on the exam itself, the JN0-481, that's the official Data Center Specialist JNCIS-DC exam. It's usually, 65 multiple choice questions. You get 90 minutes. But like you said, we're not worried about passing. We're just using its structure. It's like it helps reveal these key insights into how today's really complex data centers actually work and how they're managed. It's kind of like finding a map where each X opens a door to understanding something important.
Exactly. And that's the cool part, right? Taking what looks like maybe dry exam prep and turning it into, actual practical understanding. So let's peel back those layers, see what interesting facts and powerful ideas we can dig up. Okay, let's unpack this. First up, let's talk about something that sounds like it could really change network operations predictive troubleshooting. So when we're talking about Apstra, this intent-based networking platform, what exactly is the function of its probe tracing feature? What's it really doing in there?
Right. So the key thing with Apstra's probe tracing is it moves beyond just reacting to problems. Instead of just digging through logs after something breaks, it performs a synthetic trace. Its purpose is to validate data path connectivity proactively.
Okay, a synthetic trace.
Yeah, think of it like this. Normal troubleshooting, it's like detective work after the crime. You're looking for clues, right? Probe tracing is more like a network health scanner. It sends out these simulated packets across the fabric, mimicking real traffic to check the actual data path between 2 points you care about.
Ah, I see. So it checks if the path is working as you designed it.
Exactly. It helps you see if the network is behaving as you intend it to. And crucially, it can find things like misconfigurations or maybe a broken link before your actual user traffic hits it.
Right, before anyone notices.
Precisely. It shifts you away from that reactive firefighting mode towards, well, truly predictive intent-based management.
That sounds incredibly useful for catching things early. But, is there a risk? Could all that probing create its own noise, maybe affect performance, or just generate too much data?
That's a fair question. Is there overhead?
Yeah.
Well, the design of these probes is specifically meant to be lightweight. They're optimized to minimize impact. The whole idea is they validate connectivity without adding a significant load. And the results, they're shown right in Apstra's dashboard, so it actually simplifies analysis rather than just creating more raw data you have to wade through. It's about smart, targeted checks.
Okay, smart validation. Makes sense. So Apstra helps us know the network's behaving. But how does the network itself, learn where everything is, all the devices, the paths? That kind of brings us to a really fundamental protocol, doesn't it? In these EVPN fabrics, what's the main protocol used to share all that MAC and IP reachability information?
Ah, the workhorse for that job. That would be BGP, the Border Gateway Protocol.
BGP.
Now, if you connect this to the bigger picture, in an EVPN VXLAN fabric, BGP isn't just for the big wide internet anymore. It's a powerhouse inside the data center, too. It acts as the main control plane protocol. Its job is specifically distributing MC and IP address information between different VRFs, those virtual routing and forwarding instances.
Graphs.
And this ability is absolutely vital. It's what allows for really efficient and, importantly, scalable Layer 2 and Layer 3 connectivity across the whole data center fabric, no matter how big it gets.
It's still kind of wild to me that BGP, which we usually think of for gluing the internet together, is the go-to for this job inside the data center. Seems almost like overkill, but obviously it's not. Why BGP? Why is it so dominant here?
Well, it really comes down to that scalability and flexibility you mentioned. Older Layer 2 protocols, they just don't scale well in these massive data centers. You run into all sorts of issues, like remember spanning tree complexity?
Oh, yeah. Nightmares.
Right. BGP, on the other hand, it has really robust policy controls, route filtering. It can handle millions of routes. It provides a much more scalable and stable control plane. It was literally designed for huge scale route distribution. So its proven capabilities just make it a perfect fit for the dynamic, expanding needs of a modern DC. It gives you that massive capacity, even for your local trips.
Okay, that makes a lot of sense. Scalability is key. All right, let's circle back to Apstra then. Think about design this time. Consistency is always a huge challenge when you're building big networks. So inside Apstra, what's the component that lets you logically define things like interface roles, speeds, and what they should connect to for each type of device?
The component that tackles exactly that is called a device profile. And this really gets at how these automation platforms simplify complexity, doesn't it? Device profile in Apstra isn't just like a static list of ports. It's more like a smart template.
A smart template?
Yeah. It specifies the logical role of an interface. Is it connecting to a server, another switch? What speed should it run at? What type of device or role should be on the other end? Think of it as a reusable blueprint for configuring devices.
Ah, okay.
And the real win here is that this abstraction helps enforce consistent design rules across potentially different hardware platforms that do the same job. That means you get predictable, validated configurations automatically, and it massively cuts down the chances for human error.
Device profile, enforcing consistency across hardware. That really is interesting because configuration drift, keeping everything aligned, that's always been a massive headache, right?
Oh, absolutely.
So how much does this really simplify things?
Yeah.
Designing, maintaining these huge networks, what kind of mistakes does it stop?
It's honestly a game changer. Think about it historically, configuring thousands of ports across hundreds of switches. That was manual, tedious, and super error-prone.
Lenny.
Exactly. One typo could take down a whole rack, or worse. Device profiles kind of eliminate that class of error. You abstract the hardware, define your intent once this port connects to servers at 10 gig, and Apstra applies that intent consistently. It prevents misconfigurations at scale, ensures every single port is doing what it's supposed to, and it drastically speeds up deploying new racks or even entire data centers. It builds reliability in from the start.
Wow. Building in reliability. That's powerful. Okay, let's dive a bit deeper into EVP and VXLAN itself now. Specifically, how it handles segmentation, keeping things separate. What's the specific purpose of route targets in an EVPN VXLAN setup? Sounds very specific, but important.
It is specific and definitely important. The purpose of route targets is they control the import and export of VPN routes between different VRFs.
Okay, controlling import and export, how?
Well, what's really fascinating here is that route targets are actually BGP extended community attributes.
So tied back to BGP again.
Yep. Think of them like digital policy tags. They get attached to routes. And these tags dictate which VPN routes are allowed to be shared with and received by different VRFs. This whole mechanism enables really granular policy-based routing decisions. It's absolutely crucial for segmenting traffic properly, say, between different customers or different departments using the same physical network.
Policy tags. Okay, so that's fundamental for security and multi-tenancy, isn't it?
Yeah.
Keeping tenant A's traffic away from tenant B's.
Exactly. It's all about that logical separation on shared infrastructure. Imagine like an apartment building. Each apartment is a VRF, a separate tenant space. Route targets are like the access keys. They determine which doors you can open, which other VRFs or shared services you can communicate with.
Without them, traffic could just wander anywhere.
Potentially, yes. Or it would be much harder to control. Route targets provide that precise control. They ensure only the routes you explicitly allow are exchanged between VRFs. This maintains strict isolation and gives each tenant the feeling of having their own private network, even though they're sharing hardware. It's absolutely fundamental for multi-tenancy and security in cloud-like environments.
Got it. Crucial piece for sure. All right, let's wrap up with something really foundational. The IP fabric architecture itself. This design is a huge step up in scalability and resilience compared to older, maybe more bottleneck-prone network designs. So, in this modern IP fabric, what's the basic role served by the spine switches?
Okay, the spine switches. In an IP fabric, they serve as the core forwarding layer. Their job is interconnecting the leaf switches.
The core layer.
Right. If you picture the topology, the spines form the high-speed backbone. They literally connect all the leaf switches below them. And a key design point here is that typically every leaf connects to every spine.
Every leaf to every spine. Okay. Why is that?
That gives you incredible high availability. There's no single spine failure that isolates a leaf. And it enables equal cost multipath routing, ECMP.
Yeah.
Traffic has multiple equally good paths it can take across the fabric simultaneously.
So better performance and resilience.
Exactly. And their main function is just handling that high-speed transit traffic across the fabric. Spines don't usually connect directly to end devices like servers or storage. That's the job of the leafs. The spines are just this super fast, always-on highways in the data center.
The ultimate always-on backbone, then, making sure nothing gets cut off and traffic flies.
Yeah.
But is there a downside? Does managing such a, well, highly meshed network create new complexities, maybe around troubleshooting specific paths or scaling it out even further?
That's a good point. While it's incredibly robust, the complexity kind of shifts, Instead of wrestling with, say, spanning tree in older designs, now you need to ensure all your BGP peerings are correct, that routes are advertised properly across potentially hundreds of links.
So different kinds of complexity.
Yeah. Troubleshooting might involve digging into BGP paths more than checking layer 2 loops, but honestly, the benefits you gain in predictable performance, massive scalability, and that built-in resilience, they far outweigh these newer complexities, especially when you pair this architecture with automation tools, like Epstra we talked about, that help manage that underlying fabric complexity for you. It's really the foundational design that makes modern data centers possible.
We really hope this deep dive encourages you to keep exploring these topics. They're crucial, complex, and always changing. Thanks for joining us, and we'll catch you on the next one.